Good afternoon. I'm Megan Beckelay, Program Director for the Electrical and Computer Engineering Department Heads Association and moderator for this webinar on Virtual Labs with MATLAB and Simulink, sponsored by Mathworks. Before introducing our speakers, I have a quick housekeeping announcement. We will be accepting questions throughout the presentation, which you can submit using the Q&A text box. To access the Q&A box, simply click on the Q&A icon at the bottom of the screen. We will address all questions during the last portion of the presentation. Now it's my pleasure to introduce our speakers today, beginning with Chad Allie, Customer Success Engineer for Mathworks. In his role, Chad partners with university faculty in their teaching and research endeavors. The goal is to help customers discover and explore how they can use MATLAB in their work to ultimately create a more interactive learning experience and streamline workflows. Chad mainly supports universities and research labs in the Southwest US. We also have Douglas Jussaume with us today. Douglas is an applied associate professor with the University of Tulsa in the Electrical and Computer Engineering Department. He teaches the electric circuit analysis, electric power systems, radio frequency engineering, and senior design 1 and 2 courses. With that, I will hand it off to you, Douglas.
All right. Thank you. Let me share my screen. Come on. And go into the reading mode. Okay. Well, Megan, thank you. Again, my name is Douglas Jussaume, and today we'll be discussing virtual power labs using Simulink Electric. And as Megan said, I'm an applied associate professor at the University of Tulsa. Last few years, I've concentrated in courses in circuit analysis, electric power system, radio frequency engineering, and the senior design courses 1 and 2. My industrial background is in aerospace, first with North American Rockwell, and then Boeing, and then finally with Spirit Aerospace. What we'd like to do today is present and discuss the development of virtual power labs we developed for the fall courses, try to outline the background and lab philosophies we use in developing these labs and discuss some first steps. But first, the power labs were developed for ECE 3033 electric power systems. This is a junior level course required of all electrical and computer engineering majors. We cover in this course 3-phase systems, single and 3-phase transformers, DC, AC motors, and generators. This lab course does not have an independent lab course associated with it, so we've incorporated the labs into the course itself. We have 4 basic hardware labs, a lab introduction, where we make use of a single-phase transformer and complex loads, a 3-phase system, where we make use of a 3-phase transformer and transmission line, a DC motor lab, and an AC synchronous generator lab. We are a small department, roughly 130 students, and the lab area for the power labs consists of a single benchtop area loaded with different modular equipment, motors, generators, transformers, transmission line, and complex loads. We also have the ability to make torque and speed measurements, and we've made use of TI's 3-phase electronic meter to go and help us display real reactive apparent power, power factors, RMS voltage and current, torque, speed, and frequency. And of course, the lab's objectives is, of course, to provide the students experience in connecting together the system components or circuits, performing measurements over a wide range of inputs. And for me, I really want them to gain insight in relating the classroom equivalent circuits that we use in the power class to hardware performance. And of course, the student favorite is to write professional grade lab reports. So why change to virtual power labs? Well, COVID. With the university restrictions and the lab area and equipment restrictions we have, we realized that we would get into a logistical nightmare in trying to put our students through the hardware power labs. So our solution was to develop a virtual lab. Now, this is quite a challenge for me since I have no prior experience with MATLAB or Simulink at all. So our timeline, basically last May, after we completed the spring semester, and we all began to realize what we would have to do to cover the fall semester classes, we selected Mathworks Simulink to help us develop our virtual power labs. We met with Mathworks and we made use of their kind offer to download free MATLAB and Simulink. And so sometime in June, I started to learn and develop these labs. The first two labs we developed make use of Simscape Electrical. And then as we continue, the last two labs that we developed made use of the specialized power system components. And then this fall semester, starting in September, we introduced the labs to our junior class. So what was our philosophy in designing these labs? Well, I'm an old engineer, and what I was wanting to do is try to mimic the lab experience. That is, the students in a hardware lab would make a change, and then they would see that change propagate throughout the system. And with our use of a large screen TV, we're able to do that in our hardware lab. They can see all the different components, voltages, currents, powers that are going on as they make these changes. So the main part of the philosophy was to mimic this hardware lab experience. We would have it so they would input a change, and they could see the change, input a change, see the change. And we also wanted them to have them be able to play with the system, make different changes and get a feel for what was going on. So our lab design process, standard engineering design. We developed the conceptual design outlining the major components, input parameters, and performance data that we're interested in. Then we went into detailed design where we built the model and completed the layout. And of course, during this time, I spent a great deal of time conferring with Chad. In fact, we had a number of Saturday morning meetings trying to help me work through the different issues with developing these labs. And then for me, important part was to be able to verify the model performance using all the equivalent circuit models we have in class. Could we go one for one? Simulink made the calculation. Can I duplicate that using equivalent circuit model? And we're able to do that. And of course, the final part was to have a final design release by reviewing the model and its performance with the department chair and the faculty. And of course, like most department chairs, as soon as you showed him what could be done, he wanted more. He wanted us to look at additional model to work for a power electronics lab, power systems lab, and so forth. Now, this gives the details of each of the individual labs. And one of the consistent things we've done in each of the labs is have a control panel. Control panel does two main functions. One allows you to control parts of the individual lab. And then it would also allow you to see what the results are, what the power was, what's the current is, what the power factor is as you made changes. Now, for the lab that we're going to take a look at, the three-phase power system lab, this is just a Y-connected source with balanced load, three-wire transmission line, a parallel RLC load impedance per phase, where we measure the phase and line voltages, line current, real and reactive power, power factor, both on the source side and the load side. Now, this is what the lab looks like captured in the Simulink environment. We have on the left the model, on the right the display of the source side values and the load side values, and then below that on the lower right we have the control panel. Now let me see if I can go. And this is what it looks like live and in Simulink. So we can run the current parameters. This goes through a compiling, then pops out the numbers for that particular one. And I can turn on and off the load resistors in the parallel load. I can turn on and off the load capacitors or load inductors. Along with it, I can change the resistive values, the capacitance values by using these slider bars. And over to the right, I can change the length of the transmission line. So this gives the student a great deal of flexibility and freedom in understanding what is going on. And again, all they have to do is sit there and run it. Okay. All right. So we got a little bit of feedback from the students. And one part of the feedback was what was the level of experience in their prior use of MATLAB and Simulink, and all of them through several courses, Digital Design Lab, controls, signals, embedded systems, they've all had and were comfortable with using MATLAB and Simulink. The second question you ask, how do you feel about using virtual labs with Simulink? Did you have a preference compared to the hardware lab? Well, they felt that the virtual labs were less tedious, less stressful, but most importantly, it gave them an opportunity to test a wide range of values. However, considering all that, they still felt very strongly the need to have a hardware lab to give them the experience in building a circuit, troubleshooting it, and so forth. We also asked them, are there any benefits that you can say you saw using a virtual lab or physical one? And the biggest one was the fact that it would a good job in backing up what was being covered in class. It gave them insight on looking at a wide range of conditions and bringing home what was being taught in the course. But again, they did not feel that these were a replacement for physical hands-on labs. Now, what's interesting on these further student comments, the very first sentence up there where he says the worst part of in-person labs is setting up the circuits. You know, there's always maybe a little bit of stress in setting up a circuit, making sure it's running right, or understanding what to do if it's not running right. But they felt that that was important to give them that experience. But in terms of understanding the theory behind all this, they preferred the Simulink and virtual labs. So, what did we learn? Well, I had wanted the students to do everything one parameter, one data at a time to give them that feel. However, students being students, they really wanted to just go in, run the lab, and be done with it. So they started writing scripts to model and acquire the data without interacting with the model. I'm not totally happy or at peace with that. There's also shows areas where we need to improve what's being discussed in the lab. One lab team on a generator experiment said that the Simulink was not calculating one of the powers correctly. And when we went back and looked at it, well, we found out that they were doing a single phase, a per phase analysis, and they forgot to multiply by 3. There's also some difficulty in this 3-phase power system lab of understanding the impact of having a parallel load for each phase. Now, there are also some model limitations. They were able to, I didn't do it, but the students ran the DC motor both as a motor, as a generator without realizing it. So that's something that needs to be fixed. In the synchronous generator lab, the rotational losses are not modeled. It would be good to see if we could add that feature. Also, delta source are not allowed in Simscape Electrical. So there are things that we can do to improve the lab. Also, I did model verification based on what I thought the students would run into. Again, students being students, they came up with a few new conditions. So this is an opportunity to expand how we go about verifying the models. So what our next steps are? Well, I'd like to have more virtual power labs. I'd like to add a DC series motor. That would work very well with the DC shunt motor. I would like to add a 3-phase transformer, an induction motor, and a synchronous motor. And that would be a fairly good job in rounding out the virtual labs. Also for me, since this is my first experience with Simulink, I would also like to see what I can do in terms of developing some classroom demonstrations. And I think we need to revise the current labs and extend their capabilities. One area is a better display, not only displaying the controls for the lab or the panel readouts, but also doing more than just having a simple box representing the system. Also, since the students really want to wire the lab, could we find some way to allow them to wire the lab with maybe letting the smoke out warnings? I think that would be interesting next step. And then finally, I would like to take and integrate our current hardware specs into the Simulink models. So the students will have that comparison between what they have right in front of them to run and what the virtual performance is. And now finally, and I hope I didn't go too fast for everybody, what are my final thoughts? Well, from a professional standpoint, I've been an engineer for 46 years, and I would have to say, where has Simulink been all my career? It's been fascinating learning to use Simulink. It's been fascinating to see what can be done with Simulink, and I'm still very curious to see what other things I would like and can achieve. So I plan on continuing to expand my skills and knowledge with Simulink and working to develop a virtual lab experience. From a university standpoint, virtual labs are not going away. They will continue and will be used much more to address this changing student enrollment, allowing this to be used at virtual locations, minimizing lab costs, and providing this experience for this new generation of engineers. Okay. And finally, my email address for all those that might want to ask any further questions. Chad?
Yes, thank you, Doug. Very much appreciated.
I hope I didn't go too quickly.
No, this is perfect. I'll go ahead and begin sharing my screen then as well. All right, so, All right, so Doug, thank you once again for your presentation. That was wonderfully done. It's been an absolute pleasure working with you and getting your courses set up for virtual labs. And I look forward to more of the work that we plan on doing going forward. And so with that, I'd like to transition to this second part of the presentation. Again, my name is Allie, and the focus of my role is that I work on a team of other engineers that help support chairs, deans, professors, and researchers all around the world in helping to make sure that their departments can ultimately meet the learning objectives for their students through computational thinking and learning. And just a little quick more background about myself. Previously to working with the Mathworks, I worked for the Boeing company for about 7 years prior to this as a propulsion engineer, where I focused on developing complex fuel systems for both commercial and military aircraft. And a lot of this dealt with simulations, having to use MATLAB and Simulink as well. So with that, I'd like to transition into the rest of the topic today, which is focusing a little bit more at a higher level about virtual labs. So to start off, I wanted to have a quick discussion about what we at Mathworks have learned so far, along with our peers in the industry as well, about virtual labs and the prospect of them so far. Then I want to get into a few different laboratory approaches, looking at virtual labs similar to what Doug has just previously showed us. Thinking about hardware at home, and then also being able to access hardware from a remote location. And then once we get through that, I want to give you a few resources to help you get started with actually developing a lab, potentially for your own work. So to pick up from where Doug left off, right? I think Doug hit it very well on the head, is that because of COVID, many things have had to change, right? And so Doug, like many other instructors, have had to change their current teaching model, right? From typical doing things with having students do things with group work, focusing on hardware, and even some computational thinking in the classroom, and shift that all into an online setting in the short term because of what we're facing today. Now, we know that it's not going to last forever, and at some point we're going to get back to some sense of normal. But at the same time, because of this transition, we don't want what we've learned so far to go to waste. So in the long term, we want to take the knowledge and lessons learned from things such as virtual labs and be able to reincorporate that back into the classroom and see if we can not only improve student learning objectives, but also make the classrooms more resilient for the future in the event we deal with other situations like the current one today. And different ways we can go about doing that is focusing on the interactivity, which is some things that I'll get into a little bit later, along with pairing simulation models with hardware, and then finally even helping students to learn industrial workflows, which is some of the themes that Doug has showed. And I think one of Doug's students hit it on the head in terms of wanting to focus also on the hardware, or that the hardware labs don't need to go away. And I want to make it clear that the idea of virtual labs isn't necessarily to replace hardware labs. It can if you so choose, but the idea is to complement it, right? Is to also use it in a way in which you get the best out of all of these resources. There is no one-size-fits-all solution for having to do things in this manner. So having options definitely makes it a lot more possible for better outcomes to come from this. So to talk a little bit more about workflows, let's get into a quick discussion about some things that we've learned through talking with different academics and folks in the industry about what a typical lab workflow would be like. And so this may vary from course to course. So again, the chat is open, and we'd love to hear from you and get some perspective on how you see this model as well. But this is the workflow we're going to be working with today, and kind of how we're going to frame a lot more of this topic. So typically, if we start off in a course, right, let's say electromagnetism, right, we're going to start with some concept or idea about what this means for students when we're teaching them, right? And then we want to move into the next step of theory, right? So to reinforce the concept, to help students grasp or get a physical understanding of what this concept means, we introduce math or mathematical representations of this theory, of this concept, to help drive home what it really means and what its purpose is in real life. And this is typically all done during the class lecture. Then we move on to the lab portion of the course, right? Where we focus on actually testing out this theory, actually being able to understand the behavior of these mathematical equations, so that students get a better intuition of, again, what this concept really means to them in the real world, and giving them some focus on application. And then taking it one step further, whether you end up building hardware to be able to work more with these different kinds of concepts, or you expand on the different types of experiments you can do to, again, build further intuition on these different concepts. And then finally, students will eventually come together and put things into a report to where they can either return it back to the professor for grading, or use it as a next step to roll into the next concept that's going to be introduced. So using it as building blocks, if you will. Now, this is the typical workflow that we've come to understand for in-person sessions. Well, so what does that look like? You might be wondering what that looks like to go into an online setting. And so that's where we come to talk about our different laboratory approaches, right? Where the first one being the virtual one, which is what Doug has showed you in regards to focusing on purely the simulation environment, where you don't have any hardware involved, but you can still teach some of the same concepts. The other one is hardware at home. So think about kits, or you can think about breadboards or any other kind of hardware equipment that students can take home in a portable fashion and actually be able to complete their lab work away from the campus. And then there's remotely accessed hardware. So think about labs on campus where students can actually access the hardware in those labs from a remote location and be able to complete their work in that manner. So these are from the discussions that we've had with academics and other folks in industry. These are some of the different areas in which we've come to understand to be part of different laboratory approaches. And they all have their own benefits. Again, the idea here is there's no one-size-fits-all solution. So what you see down here are criteria that you should definitely weigh for different approaches. When it comes to learning objectives, for instance, for your course, what do you want to weigh more on, right? Teaching students industrial workflows to get ready for getting a job once they graduate, fostering collaboration so that students are working more in groups and they get more exposed to that, so that by the time they get to their capstone courses, they're ready to integrate in that manner. Maybe it's even cost. Maybe it becomes costly to afford a lot of these large hardwares, and therefore you have to shrink the size of your lab courses. But then there's also how much realism and complexity can you bake into these types of labs? So again, there's different areas in which you have to think about in order to figure out what's going to be the best, if not a combination of, for your specific course. So with that, let's transition into talking about, let's get into some of the actual examples that we have for some of these labs. So in this first approach, we're going to be looking at a virtual lab similar to what Doug has done. And we're going to be focusing on RC circuits. The idea here is we're going to introduce the concept of RC circuits and basically use a lab to reinforce those ideals. So starting off, again, we're starting off with the concept of RC circuits. Then we're focusing on some of the theory behind it, moving into experimentation, getting students familiar with what this theory means and how it works, what its behavior is, letting them further experiment or build on that foundation, and try different experiments, right? And get more experience with this concept. And then finally create a report to be able to be turned in for credit. So what we're going to do is we're going to take a look at this notebook, right? So here is a notebook that we can take a look at that has an example of an RC circuit development. So think of this as, let's say we're all in lecture right now. We're all in the lecture part of our course. And so I'm using this as my means to teach for the lecture. So here I'm giving you the title, I'm letting you know what we're talking about. And I have a table of contents that gives all the information you might need to think about it. This is all set up to support both the course and both the lecture and the lab. So I'm giving you an introduction, we talk about some theory, and then we end up getting into some experiments for this RC circuit. So let's go ahead and get started with the introduction portion. So again, we're introducing the concept, we're getting the idea of what an RC circuit is, what it's supposed to do, and then we're getting into a little bit more of the theory, right? We also talk about our learning objectives as well, but we get into the theory where we can actually visualize now of what an RC circuit might look like. And from that theory, we typically have mathematical representations to help us better understand that behavior. And so here you see some of those equations written out in a typical mathematical format. And from here, we want to start thinking about, as a student, right? As a student going through this and understanding it, and as it's being presented to them, they want to be able to understand how they can actually begin to visualize this information, right? Because it's one thing to write these equations, but it's another thing to visualize it to help you understand where this is going and what it actually means. So after you've derived some equations of, let's say, current and voltage, because those are typical parameters that we want to look at when we're focusing on a circuit, we can add in some initial conditions to make things simple, so that we can actually plot that information or visualize that information rather, and get a general idea of what's happening. So in just that short amount of time, we have talked about our concepts, we've built up a bit on the theory, and now we're actually to the point of visualizing what this actually means. It's now that we can transition from our lecture to our lab portion, where we can focus on the experimentation, giving students a little bit more hands-on freedom to go and try out these concepts and get familiar with them. So here, I have some sliders that focus on changing the resistance and the capacitance. And so you can see the two visualizations to the right, and students can use these to build intuition and understand how it's going to change based on these changes in the values, to get some understanding of what happens in the system, whether you have a high capacitance or low capacitance, or whether you have both a high resistance and a low resistance, and even changing what the voltage source is. So this gives students a little bit more understanding of what the assumptions and limitations, and ultimately what the characteristics are of this concept. Once students can do that, they can now move in a little bit further into deeper levels of experimentation, right? Or even further building something that represents this theory. This is the part where we can go into the actual virtual lab content, right? So now we're focusing on using a virtual model to start building on what we've just learned so far as a student. So here in this virtual model, right, now I have a representation of my RC circuit. Right away, I can see things that represent my resistor, my capacitor, something for my voltage source, and even a switching output that allows me to define how my capacitor will charge and discharge. And so with this now, I can start with more of my experimentation, right? So let's say I want to see the system for what it is right now. And in a real lab, as a student, I'm going to take a voltmeter and an ammeter to actually measure my voltage and current at each of these different nodes. Now, with a virtual model, I can simulate this, which executes all those equations that we were looking at earlier. And I can actually take a look at the results from this model. And this would be the equivalent of actually looking at a voltmeter reading or an ammeter reading. And so I can see the current and the voltage of both my capacitor and my resistor, and gain some understanding of how it's charging and discharging, right? And let's say as a student now, I want to add more to this model. I want to try new things. I want to expand, right? Right now I have a resistor and capacitor in series, But as you can see here, there's another component that's not a part of the circuit right now based on its coloring that I can add to this system and now have another resistor R2 with that's now in parallel with my capacitor, which changes some of the dynamics of the system. So again, if I simulate this virtual model again, I can take my readings from my voltmeter and ammeter, and I can actually take a look and see what things might have changed against my capacitor, my resistor, and even what the behavior of my new resistor now is in this system. And so with this, the benefit here is that you're no longer limited to the amount of the amount of physical parts or hardware you have in your lab. You can now add new things to add different concepts and ideas and further expand on the learning within this virtual setting without having to necessarily spend additional resources to get some of these. And so with that, you may be wondering, well, what can I do to now add more to this, right? Since all this has already been here, or it existed already. Well, here in this library, here at the top, I have the ability to add more components, right? So I can add things like diodes, gains, different kinds of controls, different motors, similar things that Doug was showing previously to further enhance the model and further give opportunities for students to explore more. And similarly, I can even add things such as dashboard components to make this more interactive, make it more engaging for students, right? Changing dials, moving knobs, things that you would do in a typical realistic lab to give it more of that kind of feel. So I'm sorry, there was one other thing I wanted to show you as well. So now we've talked about looking at the model, running a few experiments and getting familiar as students begin to build more intuition about this. You can dig deeper now. You can look at this as this notebook as a lab report, right? This is your setup to actually add more data from the models that you've run, your virtual labs, in order to capture more data from the different changes that you make to the model. So, for instance, this next experiment talked about adding a component to the circuit. Well, I just added another resistor, right? I can actually go now and look at what the change was there versus on a voltage or current type of change, and see and understand the behavior that changed, and then even start talking about things like, making some observations, like understanding what changed because I added that new component, right? Or furthermore, even changing the switch frequency, right? So that pulse change that allows how long the capacitor charges and discharges. I can go ahead and change that by a factor of 10, let's say, observe what's happening in my virtual lab, and actually add new comments to help to talk about what I'm seeing and what I'm understanding as a student. And again, continuously building and building on these concepts as you get more and more complex. Right now, we're talking about switching the frequency even higher, and then getting students to really start thinking about things such as, the mean voltage at steady state, or concepts like voltage ripple. And then even taking it one step further, right? This is all looking at things from a direct a DC perspective. Now we want to look at things from, let's say, an alternating voltage perspective, right? An AC supply. We can change our model, our virtual lab, to be able to run an AC supply, let's say at 50 Hertz, and then have students really talk about what do they expect to see in the load and why do they expect to see it, right? This is all reinforcing concepts that either have been learned previously in other lectures or maybe in this lecture itself. And further, and again, taking it one step further, right? Adding diodes and understanding the rectifying circuit, and then even looking further into voltage ripple. And so now, at this point, you've started with a very general concept of RC circuits and moved that to something further within a way that students can now understand more about what this RC circuit is doing and what its purpose is. And by building that much kind of intuition, now you have in your conclusions, you can start talking about asking students, well, what are these applications that you can put towards RC circuits now that you have a better understanding of how they work and how they operate. And once you've added all your information here, this can just be used as this notebook can be used as your own lab report. And you can easily do that by one click of a button by exporting it to a PDF. Now, what that looks like is a very similar view of what you saw already. It's the same notebook. However, it's been set up in a way that it contains all of your code and all of your output, all the experiment that you saw after you ran your virtual lab. So if we go to, let's say, our first experiment, we can see this output and even start making some comments about what's happening and why it's happening. So here now you have something that students can either collaborate on, share with their other colleagues, or even provide it to the professor for easy lab grading. So now just to wrap up this specific demo, again, we want to focus on the same workflow, right? We introduced the concept of RC circuits. We talked about the mathematical representation behind the theory. We focused on allowing students to look at the different behavior of that theory by experimenting with it with interactive sliders. We allowed them to experiment further with building different, working with different experiments to build better knowledge about the usage of RC circuits and how expensive it is. And then we actually created and generated a report in order to make that possible and finally turn in for submission. And just for your information, these are some of the products that were used in the process of developing this example. The notebook that you saw is called Live Editor, and that's what allows you to create an interactive notebook and also generate a report from one click of a button. And then also Simulink and Simscape Electrical were some of the blocks that were used in the virtual lab to develop it, very similar to what Doug has done in his own labs. So changing gears a little bit, I want to talk about another lab approach, such as hardware at home, right? In this specific example, we're focusing on the concept of deep learning using a device such as a smartphone, right? So in this specific example, we want to talk about how you can introduce deep learning to students, being able to set up your mobile phone to be able to use a pre-trained network, deep learning network, to recognize and see objects, and then finally be able to explore it even further and see how it actually operates once you have it already set up. So I'm not using the hardware today, but what I am going to show you is a specific example that's directly from our website that actually contains the process to actually run this specific example. Now, I know we're talking about deep learning because that's specific to this example. However, you may not be either teaching deep learning, you might be teaching something else specific to your course. So let's not focus so much on the deep learning aspect, but more so on the hardware aspect and what you can do with that hardware. So for example, with my smartphone that I have, I can, if I'm doing deep learning, I can access the camera, right? And that's what I want to do because I want to be able to recognize images. I want to take images and actually classify them. Now, there's more than one sensor on a smartphone. So you can set up your lab around all these different types of sensors or depending on the hardware that you're using, right? Such as acceleration sensors, angular velocity, orientation, and GPS signals. Now, you could do things such as developing a step counter or even a heart rate monitor. And those things are also options for your lab, right? So it really depends on the data that you're trying to use and how you want to use it. And even further, you can take this same kind of information and do signal processing later. So you have options in how you can utilize hardware within your lab space. And so moving forward, right, following the same deep learning example, we're initiating our camera, our specific back camera. And then what we're doing next is we're loading up a pre-trained network called GoogleNet. Now, the benefit here as a professor or researcher is the fact that you don't have to develop your own network to get started with deep learning, right? You have a pre-trained network that you can use that's already accessible to you for just getting started and understanding more about how it works. And so in this specific example, right, we're using our camera to take an image of a coffee mug. We're going to resize that data. We're going to do some processing of that data. And then we're going to feed that to our actual deep learning network and let it classify it. And when we do, it's going to let us know that it's a coffee mug. And so there are other options here aside from a coffee mug. They even have a wallet that's something that can be read in. But the idea is this was a very short example of how to get started with deep learning and understand how you can use it directly at the, in the palm of your hands. So now just to summarize this, right? So at least in the course, you can start by bringing up some concepts of deep learning, right? You can use a piece of hardware like a smartphone that has many different sensors that you can use in order to access, such as the camera, for deep learning. And then you can use pre-trained networks that actually help you identify and classify those specific objects. And just as another FYI, the products that were used here were MATLAB, also MATLAB Mobile, which is basically using MATLAB on your smartphone so that you can access these specific sensors, and the deep learning toolbox for the pre-trained network and the classifying. Now, again, your smartphone is one thing. However, there are other options for use of hardware. We also work with low-cost hardware such as the Arduino Engineering Kit and Raspberry Pi, but at the same time, also we talk to very also industrial level devices and robots. So with that capability of being able to talk to different type of hardware, you can do things such as live data streaming. You can generate code and actually implement it onto a device such as the Arduino Engineering Kit. And also, this could be great use for project-based learning. So these low-cost devices would also be a great opportunity to further explore opportunities within your lab course. And so on our website, you can feel free to check out more of those different what different types of hardware that we actually talk to. So in our last approach, I want to discuss now our remote access hardware. This is an example directly from the Georgia Tech Robotarium, where the idea is they want to be able to provide unlimited remote access to industrial robots. And so with this, what I'm going to do now is I'm going to show you a quick video of what they actually did to get this all set up. But the idea is they want to introduce robotics, right? They're going to provide you an opportunity to get familiar with a simulator, and through that simulator, you can actually test your control algorithm on these robots in this lab. Then once you actually get through it, you can start executing your code, iterate, and try and make it as smooth as possible until you get the desired behavior that you're looking for. And finally, once you're done with the robots in that lab, you can then take that data, the video feed and other sensor measurements to do post-processing however you choose. So let me adjust this briefly. And we'll go ahead and show this video.
The Georgia Tech Robotarium is a remotely accessible swarm robotics testbed.
The Robotarium is located in the Van Leer building, which is here in the center of campus. It's also home to the School of Electrical and Computer Engineering.
We have 100 ground robots, differential drive, and 25 flying robots.
Anyone in the world can go online to our website, robotarium.org, and upload code which will be executed on real robots within the Robotarium. One of the special things about the Robotarium is that it's free to access from across the world. So it does not matter if you're a high school student or an undergraduate or a teacher, the Robotarium is completely free to use.
It allows researchers that maybe don't have the means to build a huge robotics lab to actually test their algorithms in real robots at no cost.
One of the cool things about the Robotarium is that it is operational 24/7, which means that there are users from all across the world submitting experiments at any point of time.
Researchers from every continent but Antarctica have used the Robotarium with their experiments.
It's amazing to have these robots operating all the time in a room right beside where you work. That's just a special feeling.
All right. Let's just make sure you get the share back. All right, so what you saw there was just another way of remotely accessing hardware from a centralized lab for anyone to have access to and be able to execute their code on different robots so they can actually set up their code in a way that makes it more efficient and robust after doing much testing. So it's a great opportunity to get involved with some hardware that may not be available to a wide array of students if you have one specific lab for it. So again, the idea here is the idea of introducing concepts of swarm robotics, being able to develop code and implement it on specific robots, and then test that code and iterate until you can refine it until the behavior is actually achieved that you're looking for. And again, in this specific example, MATLAB was used to deploy that code directly to these robots. So now we've gone through some of the different laboratory approaches that we've come to understand throughout our interactions. I'll give you a few resources to help you get started with even developing your own lab if that's of interest to you. So the first thing is our educators page. Now this is a great resource for everything and anything you need for teaching with MATLAB and Simulink. With our instructional resources, there's things like free on-ramps that get you started with their 2-hour courses that are modular, available online for free that you can use to learn different areas such as data science and MATLAB and even Simulink in itself. There's also our courseware where you can download and look at different materials that other professors from around the world have created for teaching MATLAB in their own classes. We have various disciplines throughout the engineerings and the sciences. And even instructionals on getting started with like Live Editor, for instance, so developing your own notebook, right, for labs and things like that. We also have the virtual labs and projects section where there's actually some case studies and stories from different universities that have actually implemented their own virtual labs. So I definitely encourage you to check those out and see what other universities have been doing, along with getting some ideas and examples of ways in which you can start yourself. And then finally, there's the online assessment section that focuses on automatic grading for MATLAB codes. This would be great if you're using and teaching MATLAB in your course and you want to help out on grading. This is a product that helps automatically grade your MATLAB code. It allows students to get feedback instantly so that they can actually understand what they're doing and if they're doing anything wrong. You have analytics to be able to understand how your students are doing in your course. And then finally, there is also the capability of connecting this product with your learning management system at your university. In addition to that, there's also the distance learning community where you can collaborate and get involved with others who are teaching at a distance or even teaching online with MATLAB and Simulink. This would be a great place to collaborate with your peers from around the world to better understand what people are doing, share your experiences, and hopefully even build a better community overall. And also, it would help us to also understand the feedback from you all so that we can also continuously better our products. So finally, just to talk about some key takeaways from today's session. Again, there's no one-size-fits-all solution, so you have to balance out what the objectives are of your course and how you want to implement specific types of lab approaches that can help you, so whether it be virtual, hardware at home, like we talked about with the Arduino, or even your smartphone, or even the remote access hardware, right? Second, definitely explore the MATLAB and Simulink based resources that are available. I talked about a few of them, but some of the ones that I want to highlight are the Teaching with MATLAB on-ramp that gives you a 2-hour walkthrough of using the online grading tool, the live editor to be able to create notebooks, Simulink, and many others. And then finally, the free on-ramps that I just discussed earlier. And then last, share your thoughts with the deep learning, with the distance learning community, as this will be beneficial for the community as a whole as we continue to transition in the long term with creating more resilient classrooms. And with that, again, Doug and I are the ones that have presented today. Here's our email if you want to talk about more about what's happening in today's presentation. If you have any questions about MATLAB and Simulink, please feel free to reach out to your relationship or account manager for MATLAB, or even a customer success engineer like myself that supports your school. If you have any technical issues with what you're doing with MATLAB, our tech support is always there for support. And then lastly, Sumit Tandon is also the Mathworks liaison for ECE. And so if you have any questions thinking about from a high level, whether you're thinking about doing virtual labs for your department, Sumit would be the best person to contact, as he can get you all started in having those discussions and figuring out where we can move from there to partner together. And with that, I'd like to end the presentation and start our Q&A.
Okay, well, thank you, Chad. I would like to remind everyone at this time that we are still accepting questions. Please go ahead and utilize that Q&A icon at the bottom of the screen if you do have any additional questions. And we do have Amy and Sumit here from Mathworks to help moderate the Q&A. So I'm going to go ahead and hand it off to you, Amy.
Great, thanks. Starting my video. Thanks, Megan. Okay, I know we've been answering some of the questions via the question and answer kind of chat area, but I do see that we have one that came in from Miguel. Do you have resources to use and interface MATLAB with our LMS like Blackboard? I don't know, Chad, do you want to take that or?
No, absolutely. Yes. So the answer to that question, Miguel, is yes. We do have those resources, and the online grading platform that I mentioned, MATLAB Grader, is what you can do to actually integrate your learning management system, such as Blackboard.
And then I'm just scanning through the. I know there were some, Sumit, I know there were some questions that came in earlier that we kind of, I know you handled via the chat, but did you want to cover any of those just to share with the rest of the crew that's on the line?
I do quickly see that Allie asked if we can have access to the presentation. So yes, everyone will get a copy of the presentation that we showed today.
Thank you. And yes, thanks, Amy and Chad. There was a question around Simscape Electrical and some of the components, electronics components that can be that might be used for a lab of that nature. So for a topic like that, it would be super helpful if you can share your email ID with us so that we can reach out to you for a deeper discussion. So we can help you find those capabilities in the product, so you can use those in your tools. And if you don't have capabilities right now, we will be happy to work with you to find workarounds and then work towards supporting your workflows. And also on a general note about that, we will be sending you along with the files and demos, we will also be sending you a survey form. So if you would like to talk to any of the Mathworks engineers for a deeper discussion around curriculum development or converting your lab to virtual format, or any other questions around maybe research with MATLAB and Simulink, then we'll be happy to have one-on-one discussions with you. I know we have 1 minute, and there was an interesting question around simulation that Mohanan asked. I think we answered that a little bit, but perhaps Dev, you can take a deeper dive, or maybe Doug, if you want to take a deeper dive around that question simulation, you're welcome to do that.
Yeah, I believe the question was, even in a traditional hardware lab, would there not have been a simulation phase? I have provided a text response, and I think that, but I think this was addressed to Doug, if I understood correctly.
There is sometimes what we call a pre-lab, where they go through a series of calculations or simulations. So in some cases, you're right. There is some simulation that goes on even with the hardware lab.
Thank you.
Thank you.
Any other questions from anyone that we haven't addressed yet?
Oh, I am seeing a few come in. I know we're about out of time, but I know we could follow up after too. There was a question about, can we use smartphone sensors with MATLAB on a real-time basis?
So can you describe what you mean by real time? Is that Allie? Yes.
That's Allie, yeah.
I mean, just to give some, I guess, perspective. So if you're trying to use your smartphone, let's say those sensors, yes, you can do live data streaming from your phone sensors in order to see exactly what's happening in real time as you're going. The term real time tends to get a little finicky when we're talking about Simulink. So I just wanted to, the reason I asked was just a clarification on what you mean by real time.
Yeah, he wrote live data, so I think that answered it.
So yes.
If I may add there, yes, so that kind of live data transmission, as far as I remember, is possible through smartphones, through the MATLAB mobile app. In the past, I've even designed like controllers for like a Lego robot using the MATLAB mobile app, and you can use a MATLAB, your cell phone as a steering wheel. So we can, and then with the Bluetooth connection between the robot and the smartphone. But happy to take a deeper dive into that with you, and then figure out the configuration and the connections and so on, and also the latest capability.
Yeah, I think you make a very important point here, Sumit, that what we've noticed working with instructors to help them with virtual labs or remote labs is that the specific needs that you're trying to address, the learning objectives that a hardware lab fulfilled that you're trying to replace, are very relevant in answering some of these questions. So to Ali's question on getting live sensor data, as Sumit said, yes, it is possible, but what is the end goal here? Is this, if you're trying to construct, say, a robot that can do surgery, yeah, you likely don't want to use the sensors you're capturing from MATLAB Mobile. But if you expect students to walk around and a few seconds later work on that analysis wirelessly from MATLAB online on a web browser, that is something you could do. So I think the way we tend to approach a lot of these things is from the perspective of what it is that you're trying to accomplish with your lab, and then map those to the features that are available rather than the other way around. So I would really encourage, if you do have some of these follow-up questions, I think in the survey that Sumit mentioned, I think we'll have a field to where you could invite us to reach out to you. And if you could share your email address there, we'd be happy to set up a conversation and learn more about the specific use case you're interested in.
Absolutely.
Sounds good. Perfectly said, Deb. Thank you. So looks like we don't have any other questions right now, and I guess in the interest of time as well, how about we wrap it up for today? And thank you everyone for very much for joining, and then please look out for that email from Mathworks and ECE as well, where we will share files and that survey form, and then We look forward to working with this community and then partnering with all of you.
Excellent.
Excellent.
Right. Well, thanks again to Doug and Chad, and thanks everyone for joining us. On behalf of ACETA, I'd like to thank Mathworks for making this ECE webinar possible. Please visit the ACETA website at ecedha.org to access the on-demand version of the webinar and other ECE webinars from ACETA. Thanks again, everyone. Have a great day.